and welcome to this video series on astronomical spectroscopy, intended to explain how astronomers know what they know. I'm Dewey Anderson. Now, this series is based on a talk I gave at the Coal Creek Canyon Skywatchers Astronomy Club. They're based in the mountains west of Denver, Colorado. And the people who attend these meetings range everywhere from professional scientists from Boulder to serious amateurs with their own telescopes to some people who just think astronomy is neat and they want to learn something. Now, the talk was motivated by a question one of the members asked a presenter at one of the earlier meetings. It was 2017, and the club had a lot of presentations about the sun in anticipation of the upcoming total solar eclipse. And one of the presenters was saying that during totality, you would be able to see the solar corona, the sun's outer atmosphere, and that the temperature of the corona was a couple million degrees. Well, someone in the audience asks, how do we know that? Unfortunately, to give a complete explanation would have taken him too far off topic, so he had to settle for a one-word answer. Spectroscopy. Now, what that probably meant was, that's too complicated for me to explain tonight, but if you want to know more, the keyword you want to Google is spectroscopy. Well, how do we know that is an extremely important question to ask.
How do we know how hot stars are? How do we know how far away they are? How do we know what stars are made of? How do we know how fast stars are moving? How do we know how massive stars are? Spectroscopy is how. Usually, there's no time to go into that in the middle of some other topic, so I decided to put together a presentation for a meeting that covered those things. And now that presentation is turned into this video series.
It's a lot of topics to get through, so it's a little like drinking from a fire hose. But I want to give you some sense of how much of astronomy, the facts we know, come from spectroscopy. Now, I won't spend time explaining how spectrometers work. We'll just say they spread light into colors like prisms do. We won't sweat the details. But I want to concentrate on the basic physics that we can exploit to answer those big questions. I think it'll give you some sense of what astronomers do. We don't just take pretty pictures.
This is the kind of picture spectroscopists take. Instead of, ooh, pretty, it's, ooh, data. Now, a word of warning. I'm going to show some slides with equations on them. If you don't know the physics or the math, don't worry about it. I'm not expecting you to follow the equations. I just think it's useful to at least see what these equations look like. Instead of just saying, there is math that tells us this, I want to be able to say, this is the math that tells us this. And I'll point out things like the T in this equation is the temperature, just to show you that, yes, the equation involves temperature. And in these equations, scientists would use that temperature expressed in kelvins. That's the scale scientists use. 0 kelvins is absolute zero. But for this presentation, I wanted to keep things in units familiar to non-scientists in an American audience. So I'll quote temperature values in degrees Fahrenheit. Now, when talking about the temperatures of stars, the values are still the same order of magnitude. Thousands of kelvins is still thousands of degrees Fahrenheit. Now, sometimes you might say, wow, that looks messy. But other times you might say, that's it? Really? That's all it takes to determine how fast a star is moving? And I'll also show some tables with lots of numbers on them. Now, don't worry about paying attention to the whole table. I just want you to see that, yep, this stuff has been calculated. I'll point out the important stuff. This series is going to be in 5 parts. Part 1 is what you're watching now. It'll just be the background stuff like, what is light? What is heat? What do I mean by the spectrum? Part 2 will discuss continuum radiation, the glowing of hot things, and what's called the black body spectrum. We'll see how that can be used to determine the temperature, luminosity, and even the distance to stars. Part 3 will discuss discrete radiation and spectral lines, what they are and how they can be used to determine what stars are made of. Part 4 will talk about the Doppler effect on spectral lines, and how that can tell us how fast things are moving and some of the wide range of things we can learn from that. And Part 5 will be a short section that describes the Zeeman effect and how that can be used to measure the magnetic fields of stars and map out the magnetic fields on the sun. So, let's get started with the background stuff. I want to establish what is light and where does it come from? What is heat? And then I'll talk about the overall spectrum of light and what part of it our human eyes can actually see. So, what is light? Over the centuries, scientists have had a lot of models for what they thought light was. Isaac Newton thought light was corpuscles, like particles that would fly along in straight lines and bounce off objects when they reflected. That model did a nice job of explaining the reflection of light and the formation of shadows. Here you can see a bunch of light corpuscles being emitted from the lower left, heading toward a short wall and a tall wall. Every place they hit, the wall looks bright yellow. The bottom of the tall wall is blocked by the short wall. It's in shadow. No corpuscles hit it, so it looks dark. I also show corpuscles bouncing off the top of the tall wall, showing how light could reflect and get to our eyes. Now, corpuscles would also be bouncing off the short wall, but I didn't bother to show those. I figured the drawing would get too cluttered. So, you can see how Newton's idea explains some of the important behaviors of light. But that didn't explain some other effects like diffraction through small openings or interference patterns that had been observed. In the 1700s, Thomas Young worked out a pretty good wave theory that did explain those effects. He said light was waves, and his wave theory could also explain shadows and reflection. Then James Clerk Maxwell came up with Maxwell's equations of electromagnetism, which showed that light was waves of the electric and magnetic fields. This electromagnetic wave model is still used today in a lot of applications. But there were other things that theory did not explain. Around 1900, Max Planck and then Albert Einstein worked out a quantum mechanical view whereby light is a stream of photons. We're back to Newton's corpuscles. But the weird thing about that new science of quantum mechanics, the science of really tiny things like electrons and atoms, is that it also incorporates the wave behavior. It's an odd, counterintuitive theory, but it turned out to be hugely successful at making predictions that match experiments. I believe it's numerically the most accurate theory in science today. For our purposes, we will ignore all the wave stuff and take the quantum mechanics approach and just think in terms of light as being light particles called photons.
Unfortunately, teaching you quantum mechanics in this video series would take us way off topic and take a lot of time. So occasionally I'll refer to some property that comes from quantum mechanics. And I'll just have to say, because quantum mechanics says so. It's my version of the one-word answer, spectroscopy.
When I show drawings of atoms with electrons going around them, I'll use the old-fashioned, looks like a planetary system, and not the more correct quantum mechanics version with electron wave clouds. The old way is good enough for our purposes. So, what about these photons? Photons have no mass, which means that they always travel at, well, the speed of light. But they do have energy. The energy is measured in units called electron volts. That's a very tiny amount of energy compared with our daily experience. But it's just right for individual photons.
Electron volt is abbreviated EV, and EV is a lot easier to say than electron volt. So that's what I'll call it. I might say you have a 2 EV photon, and that means it's a photon with 2 electron volts of energy.
That energy that a photon has comes from a change in the energy of a system, meaning pair, of electrically charged particles like protons and electrons, hence the electromagnetic nature of light. An example, a negatively charged electron, drawn in light blue, is attracted to a positively charged proton, which I show in yellow. The proton is much heavier than the electron, so even though it is also attracted to the electron, it doesn't move much. So focus on the electron. That attraction can make it so that the electron orbits the proton, somewhat similar to the way the gravitational attraction between the Earth and a satellite can make the satellite orbit the Earth. Now this, by the way, is what a hydrogen atom is. One proton with one electron orbiting around it. Other elements have more protons in the middle and a matching set of electrons in orbit. Now we'll be focusing on hydrogen as the simplest case. Now, back to that satellite. The height of the orbit is determined by how much energy the satellite has. Higher energy means a higher orbit. For a satellite to move into a lower orbit, it must give up some energy. It does this by firing a retrorocket opposite the direction of motion, so that it slows down. Some of the energy it had is now in the exhaust gases that are flying off into space. For an electron, it can move down to a lower orbit by emitting a photon. The electron has given up some of its energy in making the photon. The photon zips away carrying that energy. The amount of energy in the photon is equal to the energy difference between the two orbits. That's just conservation of energy. So maybe in a hydrogen atom, this drop might be by about 2/3 of an eV. Now, what causes the electron to do this? There are ways to induce it. Stimulated emission, that's the basis for how lasers work. But if left on its own, the electron orbiting the proton will tend to spontaneously emit a photon and drop down to a lower orbit. What causes this to happen at a particular time, we don't know. There is just a probability that it will do so over a given time interval. This is part of the weirdness that is quantum mechanics. Here's another bit of quantum mechanical weirdness. The electron is only allowed to be in certain orbits. When it drops from one level down to another, it can't drop by an arbitrary energy amount. It has to drop down to one of the allowed orbits down below. Now there's a formula that says what that energy difference is. Now the important thing to know about this formula is that the little n's, n sub 1 and n sub 2, both squared in this equation, are integers, identifying the orbits. So there's orbit number 1 and orbit number 2 and so on. So I can plug in a 1 and a 2 for n sub 1 and n sub 2, or say 5 and 3 for n sub 1 and n sub 2. But I can't plug in 5 and 4.5. The n's have to be integers. Quantum mechanics says so. And that means that there are only certain energies of photons that can be emitted. Orbit 2 down to 1, or orbit 5 down to 3, and so forth. Or, as I show here, orbit 4 down to 3, or down to 2, or down to 1, with these energies emitted. We say that the atom can emit a discrete set of energies. Orbit number 1, by the way, is the lowest orbit, and it's called the ground state. The electron cannot drop down to a lower orbit from that. More on that in part 3 of this series. In addition, you can have a free electron zipping along through hot gas, and let's say it comes near a charged particle like a proton. Then the electric force between the two will cause the electron to be deflected in its path. This too will cause the electron to emit a photon, losing that energy in the process. But now there's no quantum mechanical rule that's limiting the possible energy change to only certain levels. The electron could have had any amount of energy, and so the emitted photon can have any energy. Well, not more energy than the electron had, of course, but anything up to that. We would say that the free electrons emit a continuum of energies, as opposed to the discrete energies of atoms. It's also possible that a free electron will pass close enough to be captured by the proton. It gives up so much energy that it falls into orbit around the proton, making a hydrogen atom. And it emits a photon when it does this. And while it has to end up in one of the allowed orbits, its energy when it's free could have been anything. So that means the allowed energies for the photons are a continuum. Now, by the way, if a gas is so hot that a lot of the electrons have been knocked free from their atoms, it's actually called a plasma. This is the case in stars. In addition to electrons in orbits around protons, it's also possible for molecules to give up energy as photons. So, for instance, you can have a water molecule, two hydrogen atoms, I'll use red for those, electrically bonded to an oxygen atom in green. The water molecule itself can be vibrating. That is, the hydrogen atoms can wiggle back and forth. More wiggling means more energy in the molecule. And like with electron orbits and atoms, there are only certain allowed amounts of wiggling. This much or that much, but not in between. And like with atoms, the wiggling can step down from one amount to a lower amount and emit a photon. And that means there are only certain energies that wiggling molecules can emit. Vibrational changes in molecules are also discrete. Molecules can also emit photons by having their electrons change levels, just like in an atom, or by changing how fast they rotate. Always a limited, discrete set of energies allowed. And there's also the case of solid matter. That's an array of atoms all kind of bonded together. But they too can vibrate around their central position in the crystal lattice, like a bunch of little kids standing in line to go to the bathroom. Kind of like the hydrogen atoms in the water molecule. And they too can reduce their level of vibration by emitting a photon. Now watch this guy. Boom! Vibration decreases and off goes a photon. Because of the complicated interactions of all the atoms in the crystal, there is a huge amount of allowed energies for the vibrations. So much so that it almost looks like a continuum of energies allowed. So in review, here are some ways of emitting a photon. An electron bound in an atom can drop to a lower energy orbit. Those are discrete changes. A free electron can change energy by passing a proton. There's a continuum of energies allowed. A free electron can be captured by a proton, making a hydrogen atom. This also has a continuum of energies. Also, we can have discrete energy changes in molecules and the near continuum energy changes in solids. But we're mostly interested in atomic gases. Okay, so next I want to address the question, what is heat? The quick and dirty answer is to say that it's the motion of atoms and molecules, and then include the energy of photons. But I want to take a little time to address this in a little more detail. And for that, I want to say a few words about what we mean by energy. Energy comes in a few different forms. There's the energy of the photons. There's the energy of electrons in orbits, the energy of vibrations, and the energy of something just flying through space like that free electron. And you know that there's energy in hot stuff. That's what makes it hot. Well, for our purposes, we can say that these involve just two kinds of energy. Kinetic energy, the energy of motion, and potential energy, the energy of position relative to something that produces a force, like the gravity of the Earth or the charge on a proton. Typical examples would be the motion of a roller coaster zipping down the track. That has kinetic energy. When the roller coaster is sitting at the top of the hill just before it starts down, it has potential energy relative to the gravitational force of the Earth. As it starts to roll down the hill, it converts that potential energy into kinetic energy by rolling down the track going faster. And when it goes up a hill, it converts kinetic energy of motion to potential energy of position as it moves upward, going slower. Objects tend to have both kinetic energy and potential energy, and it can go back and forth. Satellites have both. There's the potential energy of the height above the Earth, and the kinetic energy of the orbital motion. At the atomic level, we have the potential energy due to the electron's position relative to the proton, and the kinetic energy of an electron moving through space. A free electron just has the kinetic energy of its motion. A vibrating water molecule has the potential energy due to the springiness of the hydrogen atom's position relative to each other, and the kinetic energy of the vibrational motion. And in the solid lattice, there's the potential energy due to the springiness of atoms as they move out of their central position in the lattice. And there's the kinetic energy of the vibration. And for our purposes, we'll say that the energy of a photon is kinetic. So, what is heat? Heat is the small-scale kinetic and potential energy of motion of atoms and molecules and other particles. I say small scale because we don't count, say, the overall motion of the roller coaster speeding down the track. We don't say that it's hotter because of that motion. And we don't count the gravitational potential energy from the position relative to the Earth. We don't say that the roller coaster at the top of the track is hotter. But we do count the momentary, small-scale kinetic energy and potential energy as they go back and forth in an atomic vibration. In a solid, it's the vibrational motion of the atoms in the lattice. In a gas, with atoms and molecules zipping around and hardly interacting, there's the kinetic energy of the motion, plus what is sometimes called the internal energy of the atom that comes from the potential energy and kinetic energy of the electrons in the atom. Heat conduction is the process where some atoms that are moving fast, they're part of the hot stuff, bump into atoms that aren't moving so much, the cool stuff. And by doing so, they make those atoms move faster. The fast-moving atom gives up some of its kinetic energy to the slower atom. Fast is not so fast now. That makes it cooler. And the slow is not so slow. That makes it warmer. Another thing atomic collisions can do is bump an electron up to a higher orbit. Now here comes a fast-moving atom. It collides with a slow-moving atom. But now, instead of the target atom moving fast, it recoils slowly, but its electron now has more energy. It's in a higher orbit. That's where some of the energy of the collision went. So some of that kinetic energy of the collider got converted to potential energy of the electron in the target atom. What can then happen is that the high orbit electron spontaneously drops down to a lower orbit, emitting a photon. Net effect. The colliding atom is now moving slower. The target atom is also moving slow. And now its electron is back where it was in the low orbit. Some of the energy that was in that collider is now in the photon. If the photon then zips away, the net effect is that the average speed of the atoms in the gas is now a little slower. The gas is now cooler. This process is called radiative cooling. And it's why, if you just let a bunch of warm gas sit out in space, it will get cooler over time, radiating away a lot of its energy. It's why the Earth cools down at night. It converts energy of heat to energy of photons through atomic collisions and radiates the photons off into space. In addition, things that happen in one direction can also happen in the reverse direction. Now here an atom can absorb a photon, boosting an electron to a higher orbit. Then that slow-moving atom collides with another slow-moving atom and can actually give up some of that electron energy to kinetic energy of the atoms, making them spring away at higher speed. Photon energy has been converted to kinetic energy. The atoms are moving faster, the gas is hotter. This is called radiative heating. This is how the sun warms the Earth. It emits a barrage of photons that strike the Earth's atmosphere and surface. Those photons get absorbed, raising energy levels. Collisions turn that into kinetic energy. The Earth gets warmer. Now, as it happens, when an object undergoes radiative cooling, the energy of the photons it gives off depends on how hot it was in the first place. This makes sense. Hotter objects have more electrons and atoms getting knocked into higher energy states. And so hotter objects give off more high-energy photons. The distribution of photon energies being given off is called the spectrum of the radiation. This is exactly analogous to what you think of as being the spectrum of a rainbow. we see different energy photons as being different colors. Blue and violet-looking photons have more energy than red-looking photons. Now, by the way, there is nothing intrinsically blue or red about a photon. It is the physiology of our eyes and brain that makes us perceive them as different colors. Now look at this graph. The scale is logarithmic, powers of 10, so it covers a huge range in photon energies. That's 1 EV, 10 EVs, 100 EVs, 1,000 EVs. But as it happens, our human eyes are actually only sensitive to a very narrow range of photon energies, from about 1.65 EV to 3.26 EV. This is called the visible range. And as shown here, red photons are the lowest energy ones we can see. Yellow have more energy, green even more. Then you go through the higher energy blue photons to the violet photons that are the highest energy photons we can see. Photons of slightly higher energy than our range are called ultraviolet, beyond violet. Slightly lower energy are called infrared, below red. We can't see them with our eyes. Really high energy photons are X-rays and gamma rays. Really low energy photons are microwaves and radio waves. That's right, the radio station's antenna is emitting low energy photons. And while our eyes can only detect a narrow subset of those photons, we can make instruments that detect photons at all of those energies. If there is an even distribution of photon energies over the visible range, we would see a nice rainbow if we spread it out, which is what a prism does, or water droplets in a rainbow, or a spectrometer. This horizontal line is a graph of how much light, brightness, versus the energy of the photons in that light. This kind of plot is a common way to look at spectra. We'll be looking at spectrum plots like this a lot. If we don't spread the light out with a prism, we experience it as white light. It was Isaac Newton who first figured out that white light was actually made up of all the colors of the rainbow. He spread the light out with a prism. That's an early form of spectrometer, something that spreads the light out into component colors. It makes photons of different energies take slightly different angled paths. If the distribution of photon energies is not even, say there's not a lot of high-energy blue and violet photons, then we'll perceive a color that looks more reddish. If there's more high-energy photons than low, then the color will look more bluish. So consider an electric stove burner. You turn it on and electricity starts to flow through it. That means free electrons are being drawn through the coil. As they move through, they collide with the atoms in the coil, making them vibrate. The coil is heating up. Those vibrating atoms will emit photons. As the coil gets hotter, it begins to emit more and more photons. Initially, the photons are only low energy, below the visible range, and you can't see that the burner is hot. But eventually it gets so hot that a lot of the photons it emits are actually in the bottom of our visual range. We see that as red, so the coil appears to be glowing in red light. The hotter it gets, the more photons are emitted. That means that, 1, it looks brighter, and 2, more of the photons are higher energy, more yellow photons. So the glowing coil goes from a dull red to a yellower orange glow. If it could get hot enough, like that arc welder the guy's using at the construction site, it would damage your eyes from the brightness, lots of photons, but before you went blind, you would say, hey, that looked blue, because so many of the photons are the high energy photons in our range. Okay, so that covers the basic background stuff about light and heat. Let's take a minute to review. First off, we said that light is a stream of light particles called photons. They come from changes in electrically charged systems like electrons and atoms. The energy is measured in electron volts, which I call EVs. You get discrete energy transitions, only certain allowed energies, from atoms and molecules. You get a continuum of energy transitions from free electrons and solid material. Heat is the small-scale kinetic energy and potential energy of the motion of atoms and molecules. Radiative cooling happens when fast collisions in hot stuff result in photon emission. The distribution of photon energies is called the spectrum of the light. Our human eyes can only detect photons that have energies in the range of 1.65 eV to 3.26 eV. This is the visible spectrum. And red light has the lowest energy.
That's the basic background. You're now ready to move on to the Part 2 video, where you'll learn about continuum radiation and the black body spectrum. See you there.